So I want to talk a little bit, very briefly, about translational quantities and rotational quantities in the hopes that you'll have a reason to care about today's lecture. So we've got position. I'm going to write this a little bit different than you see. This is on page 58. Problem number 10.7. So if you're looking in your book, you can have that while I'm getting ready here. So sometimes we use the symbol R vector, and I'm going to see if there's a better black marker here. We know we use V for velocity, A for acceleration, M for mass, force is a vector, and momentum is P, lowercase. Well, the angular equivalence of these, and again, we talked, there's special conditions. If you want to treat theta as a vector, I'll say rotate one axis only. We're restricting ourselves to that so that we could treat it as a vector. What was angular velocity? Do you remember?
The little fish, right? Well, no, that's acceleration.
And that's alpha
Of
omega. It looks like a W.
yeah.
Yep. Mass is something new, and that's what our lecture is today. It's called moment of inertia. You could call it the rotational equivalent of mass. I'm going to get lazy sometimes and say rotational mass. Okay. Well, instead of force, we're going to talk about torque. And hopefully we get to that by the end of class today. If you're a mechanical engineer or a civil engineer, sometimes you're going to hear the word moment, but more on that later. Engineers tend to call torques moments. We call them torques. All right. Momentum. Angular momentum is equal to L. Okay. And then maybe I'll mention one more thing here. It turns out you probably already know an equation for force. F equals MA is the first equation that jumps into your mind, right? What do you think the equivalent equation would be? And I guess to be fair, it's the sum of forces equals MA, right? The net force equals MA on an object. Well, the rotational equivalent of sum of forces would be sum of torques or sum of moments equals, what's the rotational equivalent of mass? Moment of inertia, what we're going to talk about today. What's the rotational equivalent of acceleration?
Fish.
Alpha, fish swimming left. There we go. So we're going to spend some time making sure we can understand moment of inertia because it's used to help us understand rotation. All right. What's momentum? What's the equation for momentum?
Mass times velocity.
What's the equivalent for angular momentum?
Moment of inertia times omega.
Exactly. Another spot where this shows up. Maybe I'll mention one more equation. What's kinetic energy? I'll call this kinetic energy 1/2
Oh, 1/2
mv squared. Well, what's rotational kinetic energy? We're going to use the same symbol K. It's kinetic. What would the equivalent be?
1/2 moment of inertia. Omega squared.
So my point in showing you this chart now is for this purpose. We're going to spend about 2 hours talking about moment of inertia till you're bored out of your mind. But in my opinion, look, if you can't get the moment of inertia right, that'd be like saying you can't figure out the mass. And then you'd be worthless at trying to do force problems, right? So unfortunately, we kind of have to know how to figure out the moment of inertia. Otherwise, we can't do anything else in rotational. Is that clear? We did rotational kinematics. That's as far as you can go without moment of inertia. Look at page 59. In particular, at the top of the page, notice what it says in bold. Look at this cool coordinate system Don got me first. Isn't that crazy? X, Y, and Z. Gouge students' eyes out while you're telling them the Z axis. Boy, that'll be cool. What does it say? Moment of inertia is a world of hurt. Okay, that's not a good sign. It takes 2 hours to figure out moment of inertia. It takes 10 seconds to figure out the mass. You throw something on a balance, you got it. Here's why. Let me just grab an object. Let's start with this. And you've got a couple of these, you can pass them around. I'll pass these around too. But you can imagine these two objects have the same mass. You can put them on a scale, and I don't know if you can see this. There's a hole at the center, right? This one, there's a hole at the end. And that's because this one has 2 point masses placed right at the center. This one has point masses placed at the top and the bottom, at the ends. If you just grab those two and just pass them around and try and rotate it, try doing different things. Try rotating them about the center. What about at the end? You can try spinning them like this and see what happens. Work your forearms a little bit. I'll pass these around. Try these out here. Yeah. This chart is in the solution manual filled in for the whole page. So if you need that chart with the analogy, it's in the solutions. If I'm rushing you, I apologize. So here's the deal. Moment of inertia depends on a couple of different things. Roll my sleeves here. And you've got all the notes here, so hopefully you can just have fun and listen and hit people on the head with that, whatever you got to do. The symbol is I. It turns out the units, I'm going to tell you the units right now. They're kilogram times meters squared. All right? So this is obviously different than mass. It's somehow equivalent to mass, and to make the units work out, we need these extra meters squared in there somehow. It depends on the amount of mass, the distribution of mass, the axis location, and axis orientation. That's a lot different than putting something on a balance. And let me grab another thing just so I can show you. the amount of mass matters, clearly. But how the mass is distributed? Is it distributed over a triangle? Or is it distributed over a rectangle? Or is it distributed over some weird other shape? How the mass is spread out, basically the shape. So this is a fancy way of saying what shape the object is. Is there more mass at the left end, right end, or is it uniform? Is it top heavy? Is it not? Axis location. I could rotate this thing about the end. I could rotate it about the center. I could rotate it about 2/3, etc. So the axis location will matter. But wait, there's more. Axis orientation. What do I mean by this? I could rotate this thing this way, but I could also rotate it this way, about the center. Do you agree? Right now, I'm rotating this thing lengthwise about the center versus out of the page about the center. That matters too. Is that okay right now? Basically, whether you use the X, Y, or Z axis. And you might be saying, well, what if we use some other weird axis? Yeah, let's focus on the basics, right? Let's just focus on rotating about X, Y, or Z. You could do diagonals later. Okay? There is a table given to you on page 59. You will get that table plus a few extra things on your test day. And you will have a chance to see that. So if you look at the equation sheets for test 3, they include those pictures and those equations. But I want to point out just a simple one. Look at this. Let's say we have this rectangular plate, right? In particular, if I rotate it like this versus like this, the moment of inertia is not the same. Look at the third column in your table on page 59. Do you see the rectangular plate? Let me try and do this in the same order. We have a rectangular plate with some side A and some side B. The moment of inertia about the center of mass for this particular orientation is, what was it, 1/12 mv squared. Notice it's kilograms meters squared. Versus if I take the same rectangle and put it through the center like this, the moment of inertia, oh, so much better. It's still got a 1/12 in it, but it's, whoops, there's a 1/12 times the mass. And then what is it, a squared plus b squared? Yeah. Thank you. So the same mass, we could have the same dimensions. If it's still size A and B, we get a totally different answer. Why am I spending time on this? When you're doing physics problems, look carefully at the table. There's going to be a lot of different shapes that look similar, and make sure you grab the right one out of the table when you're doing your problem. Does that make sense? In particular, I'm trying to stress, look where the axis is oriented and located to make sure you grab the right number out of the table. If you want to talk about the axis location, look at the second column. I'll get out of the way. You have a rod, it's length L. This one is 1/3 ml squared versus this one is back to our 1/12 ml squared. Notice a plate about its center acts exactly the same as a rod about its center. All right. So we could derive these results This one is an example of the axis location mattering. Here, it's at the center, oh, whoops. This is I at end versus this one, this is I at the center of mass. We get different results depending where this is located. Enough said on that? All right. All right. Let's take a look. Oh yeah, here's the other fun part. How many moments of inertia are there for a rod? An infinite number, right? There's an infinite number of ways you could change this. Now, most of the time, the most common choices would be right in the middle or right at the end. So that's why we tabulate these, because these cover overwhelmingly all the problems you need. But there's going to be a few special things that we do with this, and maybe I'll tell you the summary now. I'm going to tell you where the summary is. In case I get ahead of myself, there's a summary of what we want to do on page 64. And what we want to do is try to avoid calculus at all costs. So some of the things that we're going to do are we're going to learn some tricks and some math formulas to avoid doing calculus. And then I'll also show you the calculus. And that page 64 has a flow chart saying, here's the recommended order in which you should pursue determining the moment of inertia. All right, enough on that. Can I see those two pipes real quick? All right. So I'm looking at problem 10.8. I'm on the right website. And if you look at 10.8, that's a mathematical model of these two things. Rod 1, let's see, your book. Rod 1 is the blue one here. The masses are at the ends. Hopefully you noticed it was a lot harder to rotate, right? Yeah, this one has the point masses at the middle. So what we're going to do is try and use our first moment of inertia technique and say, well, what happens if we have a compound object? We've got a rod and 2 point masses. Let's get the total moment of inertia. So go ahead and read that. We'll get organized here and erase the board. Okay. And if you want to race ahead and use the solutions, I'm not offended. Still racing here. Ten 10.8. We have these two pipes. We're going to treat the pipe as a rod. Let me get on the right whiteboard. Got the point masses at the ends. Rod 2. Point masses at the center. And we're going to do a moment or we're going to do an axis through the center. Okay. All right. So in this case, I think we know the rod has mass M and length L. And we're told it has a radius of L over 25, in case we need that. And then the point masses, to be clear, these are the point mass. These are the point mass. What is this? The mass of the point mass is 5m. And I took these numbers straight from the specs on these red and blue. So these are actual specs of these red and blue rods here. That's the actual numbers that we are representing with these two objects. All right. We're going to treat each of those point masses as point masses. All right. Which one's going to be easier to twist? Rod 1 with the masses far from the axis, or rod 2 with the masses close to the axis? I like to bring up the figure skater. When does a figure skater rotate fastest? Arms out or arms in? In. Mass close to the body, mass close to the axis, easier to rotate. Got that? If that helps, figure skater, arms in, easier to rotate. Kind of like that, right? Arms out, mass far from the axis. That's how I think of it. What do I do with the marker? Whatever. Okay, so let's do this. Let's get the moment of inertia of object 1. Well, when I look at that, it's the moment of inertia of a rod plus the moment of inertia of point mass 1 plus the moment of inertia of point mass 2. Right? The total mass is out of the mass of all the objects, the total rotational mass or moment of inertia, add up the moment of inertia for each object. Seems easy enough. Well, what's the moment of inertia of this particular rod? In particular, grab a number out of the table on the page right above there. Which one? Is it the 1/12 or the 1/3? How do you know it's 1/12? Axis is through the center. I'm going to grab the 1/12. 1/12, the mass was m, the length is L squared. Now look up in that table for a point mass. What's the moment of inertia for a point mass? mx squared. What is x in the table?
Distance from the rotation.
Absolutely. So what is x for this problem? L over 2. How about for this one? Oh, true, but x is a distance, so we can just take the absolute value. And let me show you something else here. In the moment of inertia, we don't have to worry about the plus minus because it's all going to be squared. Because look at the formula, it's mx squared, right?
Oh, yeah.
And so then that's another thing. We don't have to worry about plus minus signs on it. It's distance. Good thing to be worried about though. So do you agree this is going to give me 2 times 5m times length over 2 quantity squared? This is 2 times mass of the point mass times x squared. I have basically they have the same x, so I could just double it.
You did it too because there's 2 of them, right?
Yeah, there's 2 of them with the same x value. Yeah, if they had different x values, I couldn't double it. Is that cool? All right, let's crank this out. And then what is that going to be? 10 over 4. Is that right? 10 over 4 ml squared. As engineers or CS majors or basically anybody except a mathematician, what might you do at this point? Yeah, punch this in on a calculator so you get the right decimal. Now, I don't know why I'm crazy like this. I'm just going to do the common denominator because that's what I tend to do. Can't help it. But in this case, we're going to get 30 twelfths plus 1/12, 31 twelfths. Could somebody punch that in real quick and get a decimal? What do you get for 31 twelfths?
2.58333.
Okay, that's good. Usually we only care about the third sig fig. Well, let's not even worry. Let's just say 2.583, right? We'll worry about sig fig some other problem. So that's the moment of inertia of rod 1. What's the moment of inertia of rod 2? Well, shouldn't it look similar? And I'm going to cheat and say 2 times I of the point mass, since we know they're in there twice. What is the value of x in this case, approximately? How far are these masses from the rotation axis? They're basically 0. All right? In this case, what happens to the I of the point mass? Remember, that's m of the point mass times x squared. If x goes to 0, what happens to that term? Goes to 0, so then I2 is that, right? So in this case, oh, whoops, I forgot to label this as I2. What is the point of all this crap? This is rod 1. This is rod 2. Point mass is at the end. Point mass is near the center. I2 has a small moment of inertia, easy to rotate. Point mass is far from the center, harder to rotate. Got it? You take another hit off that. In the next problem, let me show this real quick. In the next problem, we say, okay, what's going to be different if we rotate them both about the end? All right, so take your guess, try rotating them and see what you think about the end now. Any questions about this one while it's up here? Now I want to be clear here. Technically, you might be saying, well, x isn't exactly 0, is it? If you really are that crazy of a person, I said treat them as point masses, but they're not really point masses. At this point, they're actually cylinders, right? The masses are of a cylindrical shape. If you look at the solutions, I actually did the math treating them as cylinders, and I showed you that it's a very small correction. I think it was less than 5%. So if you're worried about treating them as a point mass because they're not, it turns out it's only a small correction. It's not a big deal. All right. Let's try 10.9 now. I'll move the board over in just a second. So now, same problem, different axis. If you had to guess, which one of these has a larger moment of inertia now? Or are they the same? What does your gut tell you? You think the second one has what, more or less? I couldn't hear.
More.
Okay, and why do you say that?
Less.
Oh, less. Why do you say less?
Because in the first one, the second like mass, like all the way at the end.
Yeah, but this one has twice the mass.
It's still closer to the axis. Right?
Yeah, but if you have twice, right? Look at this. It's half the distance, but it's twice the mass. You're right, but why?
That was just,
What quantity gets squared in all these?
oh, the length.
The distance matters more because it's squared in the calculation. So your intuition was correct. I was just trying to see what. So let's write out the equations and see if it makes sense. This one would be I1 equals 1. What's the moment of inertia of the rod for this axis? 1/3. What's the moment of inertia for this point mass up here? If the point mass is on the axis, what is its moment of inertia? 0. How about this one? ml squared. So notice out of this, what is that going to be? Hopefully I didn't screw that up. Oh, wait a minute. I did that wrong, didn't I? What's the mass of the point mass? 5m. I should have written that out. This is mass 5m. The rod is mass m and length L. So then this is wrong. The first term was right, but this should be plus 5ml squared. Right? And what do we get for I1? 5.33. Whereas over here, I still have a rod. It's at its end, so I get a 1/3 ml squared. I get 2 point mass terms. The mass of each point mass is 5m, but the length is L/2, and that gets squared. And so the 2 from doubling it gets canceled and then some. Good? Let's go ahead and do the math real quick. What is that? 10/4. Well, we could do common denominator again, or just punch it straight into your calculator, and I'm going to do that because I'm lazy. Punching it in. 1 div 3 plus what? 2.5? 2.833? Isn't that what we had last time? I forget what it was. Oh, it was a little different. Notice they're a lot closer to each other this time, right? It's not exactly double because the rod matters a little bit, but so that's why when you try to rotate them about the end, they're on the same order of difficulty, right? They're about the same difficulty. This one should be maybe about 40% easier or something like that. So far, so good? All right. And I'm doing this ad nauseum just because I want you to succeed, not because it's fun. Let's do this here. 10/10. Oops, no, it's not that way. It's through the long axis of the rod, right? Wouldn't be spending time on this if I didn't think it, these ones are in the middle, right? I didn't think it wasn't worth it, so I apologize if it's a little boring. Now we're rotating them about the long axis. Got it. This way. Blue one. Oh, geez, I shouldn't have done forearms this morning. Which one's going to be easier to rotate? Which one has a smaller moment of inertia? That's what that question is. Easier to rotate, smaller moment of inertia. Which one?
Same.
Same. All the mass is on axis, right? At this point, treating these as point masses becomes a failure. We would actually have to use the cylinder formula, but these have the same moment of inertia. So I'm just going to write I1 equals I2. Now, believe it or not, you can kind of think about this if you're a chemistry major. There's a thing called rotational spectroscopy, and the energy levels at which atoms emit light will depend on their moment of inertia. In particular, imagine if you had an oxygen molecule. This is a very crude model of an oxygen molecule. Two spheres connected by a spring. We can talk about the principal moments of inertia, about the x, y, and z axis. And if you had an atom that was rotating in some weird fashion, we could decompose that rotation into x, y, and z rotation. And we could talk about the energy associated with the x, y, and z rotation. Which moment of inertia would be the smallest? Rotating this particular oxygen molecule about the x, y, or z axis. Which do you think would be easiest to rotate? Which has the lowest moment of inertia? Rotating about the x-axis, rotating y, or rotating z? X, y. You're right.
I saw the mass through the axis.
Mass is on the axis. Yeah, if you could just kind of get that, and hopefully that was enough to get the intuition. Mass close to axis, easy to rotate. Mass far from axis, hard to rotate. All right. Moving on. If you want, you can go in there and notice what it says in 10.10. You have to treat the gray cylinders, the point masses, as discs, and each pipe as a ring. So it becomes, you have to use the cylinder and ring formulas from the table up above. All right. Let's go on to page 60 here. I'm going to erase the board. I want you to skim over page 60. Okay, skim over page 60 while I'm erasing. Anybody in here a mechanical engineer? This is huge for you, right? Things rotating. It is a big deal. All right. Only one. I love it. You think you could ever use this at coding? That's what Alan's doing nonstop right now. He's been working on moment of inertia for like a week and a half. We use this all the time, right? Anytime things rotate, right? Think about how many things in the world rotate. Moment of inertia comes into play. Alan, while I'm erasing, is there anything you might want to add to the discussion about like what helped you when you were studying this chapter or anything like that? Moment of inertia, rotation, chapter 10.
I'm not sure. I'm trying to remember, honestly.
Yeah, I gotcha. Was it hard or was it easy or did it take a lot of practice or what was it for you or just?
Yeah, it's just a lot of practice getting like you guys exposure to like always working with these pendulums because I think you're gonna see a lot of rods rotating about it too.
Definitely a lot of 1/3 and 1/12 from the rods. We use that all the time. Keep it simple, right? Yeah, and then rolling objects, right? Cylinders and spheres, we use that for rolling objects all the time. Rings, tires, right? Think about that. All right, all right. Page 60. Usually calculus is our last resort. I have to cover it first, just so you'll see why. Let me just not tell you why, just show you. Now, the image at the top of the page shows you the theoretical model of how we're doing this. The idea is you're going to take an object and you're going to build it up out of cylindrical shells. Now, before you freak out, don't worry too much. Just hear me out here. The idea is there's going to be an axis of rotation, and what you want to do is slice up this object into cylindrical shells such that all points in slice are equidistant from axis. Okay. In theory, the way to do that is to use cylindrical slices and do what's shown in the book. In practice, we can simplify things a lot and not have to worry about this. Oh, and the equation that you would use r squared dm. dm is the mass of the slice, and r is radius from axis to slice. Okay? Now, in practice, what we can do is if you have a rod, if you slice a rod up into little pieces, the cylindrical chunks we could actually model as normal dx chunks. The size of this would be dx. The distance over here, the radius from the axis is just x. So we don't have to do some scary 2D, 3D integral. Woo! Dodge that bullet. Help me out. What's dm for a one-dimensional object? Not dx, but it relates to dx. What are the units of this? This is mass. Kilograms. This is. So what do I need in here? Kilograms per meter. What has units of kilograms per meter? Upside down y is a lambda. Got it? Remember that from center of mass? Same crap. What if we do a plate? If I do a plate, let's say this is the x-axis and this is the y-axis. Here's my plate. Okay, let's put some shading in here just so it's a little easier to see. I want to slice this thing, and so let's say I want to rotate about the y-axis for no good reason. What do I mean by that? I want to rotate it about the y-axis. That's different than rotating about the x. Do you agree the distribution is different? Right? So let's just talk about the y-axis for no good reason. What's important about the slice? What must be true about our slice? I need, well, yes, oh yeah, true, but all points in the slice are equidistant from the axis. How am I going to have to slice this object if I want to do a moment of inertia about the y-axis? All points need to be equidistant from the y-axis. Would I get a horizontal or a vertical slice? What's that? No. It would be, so take a look. If I slice it like this, This is wrong. This point in the slice is closer to the axis than that point. Do you agree? So that's not valid. So then take a guess which way I slice it. So let's check. Imagine you had some cylinders here, right? Every point, right, where you have a cylinder around the axis, that would trace out this little piece. See it? That would be X. This distance is what? What's dm?
G sigma.
Sigma times what? Let's check the units. Mass is, what's sigma units? Kilograms per meter squared. So what do I have to multiply? Not dx. dA, a small amount of area. If I have a small amount of a small amount of mass, I need a small amount of area. Got it? All right, so if I have a small amount of mass, I need a small amount of distance times the kilograms per meter. Now, what is dA in this case? Remember from when we did center of mass? Not dx dy. In some problems that would work. In this particular problem, is y tiny or is y macroscopic? It's a small amount of x, I'll give you that, but is this a small amount of y or is it? Just y dx for this problem, right? The entire height of the slice. And y would equal slope x plus intercept. So the height would be some function you have to plug in. Got it?
Yeah.
Is that okay?
Yeah, I remember this from Cog 2.
Yeah, or last week in center mass, right? We just did this. Yeah, it's the same crap. And then I think I did one more, right? 10.15 shows you what if you have a cylindrical symmetry.
Never good at this. Yeah.
Yeah, I could help you with all this crap too if you want after, but like if you forget all this stuff. To be fair, I'm not going to make you do this integral in 20,000. What year is this? 2022. But for future classes, I don't know. So ask me if you're watching this video lecture 10 years from now or 1 year from now. But this is not going to be on your test. But the result of it, if you're curious, you could slice this into cylinders. And we actually use this in Physics 163. So it's not a waste of time to see this. I discussed this problem in, what is that? 10.15. So if you want to learn about this, do problem 10.15. I work it all out and I show you. It actually surprises people. But I give you this answer on the equation sheet on the test, I think, too. We could double check that later, but just so you know, I'm not going to make you derive this on the test in 2022. All right. Just cover it. You never know, right? What if I change my mind later? Okay, should we try using this information to see if we can actually do something rather than just have a bunch of crap on the board? Let's try and do something. So I'm going to do a rectangular plate, 10.11. I want to use this axis. I want to have a rectangular plate. Obviously, we can look up the answer, but I'm trying to show you how these answers are derived in case that helps you understand them. We've got a width B here. We've got a height A. Okay. And then what else? We're told uniform mass density. total mass M. I think I used capital M. I'll try to be consistent. We're going to rotate it about the y-axis. So that's the x, and this is the y-axis. I can't write it enough. Now, I'm just going to try to be consistent with what you're going to see in the future, especially for the one mechanical engineer. Crazy. This is an insane class, isn't it? Everything about it. It turns out, if you're going to rotate about the y-axis, the standard notation is IYY. Basically, the only person that probably should care about this is the mechanical engineer. I'm just showing you, this is how they're going to write it in your engineering classes too. When you rotate about the y-axis, it's IYY. The reason why is normally when you rotate, there's this big matrix. And later on, you're going to learn about that. And so you indicate whether you're in the X row and X column. That's what the two X's are for. So these are called the principal moments of inertia. And if you take Math 184, you learn about linear transformations, and you can rotate these things around, and you can take any set of rotations and put them into the principal axes. Enough said. Basically, your linear algebra class is really freaking important. That's all I'm going to say. For now, if you're wondering why I call it IYY, you could just say because he's weird. That's fine with me. All right, let's move on. Okay. Do I want to use a horizontal slice or a vertical slice for this problem? I want to rotate about the y-axis. I need every point in the slice to be equidistant from the axis. Is that going to happen with horizontal or vertical?
Horizontal.
If I slice it horizontal, is every point in that slice the same distance from the y-axis?
I know.
Nope. It's exactly the opposite of center of mass. Have you noticed that? In center of mass, when you want the x center of mass, didn't you slice it vertically? And when you want the y center of mass, you slice it horizontally. Well, if you want the y moment of inertia, you slice it y. If you want the x moment of inertia, you slice it x. As if it wasn't already confusing enough. Center of mass, you slice it basically the opposite direction. So we need to slice it vertically. Again, how do I remember this? Every point in the slice has to be same distance from the axis. Your slice should be parallel to the axis. All right. What's that?
Could you remember it as always being a cylinder when you were?
Yes, yes. Now think about this. If this is a cylinder, there'd be another slice here. But if I integrate from this side to that side with this slice, I'm going to pick up that slice when I get over there. So yeah, just imagine what that cylinder would look like, cutting it up, and then you could say, draw an imaginary cylinder around the axis, and your slice should match that. Absolutely. All right. That's x. This is dx. What's dm for a plate? Is it lambda dx, or is it something else? Sigma dA. What's the area of this slice? How wide is my slice? Dx. How tall is my slice? The Canadian slice. Sure thing, eh? So in this particular one, do you agree all the slices are A times dx in area? All right. What's sigma? What does this mean? Uniform mass density tells us sigma equals total mass over total area. Excellent. The total mass is M. What's the total area of this whole plate? AB. I've got all the pieces I need. Look at this. Now, in this case, look what this problem reduces to. Isn't this special? What happens to the A's? And we actually get mass per unit length times dx for this special case because a rectangular plate is the same as a rod as far as moment of inertia is concerned. The moment of inertia doesn't really care about the height A. I can use this, skinnier, right? But it's always going to depend on the length. That's what matters. The length is the important thing. The length tells you how far from the axis the mass is. Should we rock this out? I equals the integral of r squared dm. R means distance from axis. How far is this slice from the axis? X. So in this problem, r magically becomes x. dm becomes all that junk. What are my limits of integration? What is the leftmost value of x? What is the leftmost value of x?
Negative x.
Negative x? No. No. Negative half b.
Oh.
So, right, because x is a variable, we want to talk about. So the actual, it'd be like this. In this case, right, I know the total length is b. Well, my x could be any number from negative b over 2 all the way to positive b over 2. But so that's what my limits are. They're the actual dimensions of the objects are your limits or relate to them. So in this case, we're ready to rock. Race you, go. Plug in all that junk and do this integral. Combine the constants. I'm going to get x cubed over 3. Oh, the lower limit matters. I guess you could have said, could I do a trick here and double the integral because it's symmetric with even limits, or symmetric limits with an even function? Whatever. If you saw that, that's awesome. I think you're awesome. I would probably want to do that, but you know what? It's almost whatever time it is on whatever day it is. It's life real.
To the 13th.
I'm tired. B cubed over 8 minus b cubed over 8. That's going to be b cubed over 4. And then one of the b's cancels. Take a second to make sure you believe me that you get m over 12 b cubed, or wait, b squared. One of the b's cancels. We better get kilograms meters squared. Feeling good on that? Good, or what you are thinking? You're here. You're good? Thinking? Yeah, right. This gives me b cubed over 8 plus b cubed over 8, which is b cubed over 4. Gives me a 12, one of the B's. Over there, good? Maybe? Okay. Now here's the deal. We did not need to do this integral, right? This one is in the table. Double check, look in the table and see if that's the right result. Make sure you can find it in the table. That's more likely what you need to do on test day. Do you see it? It's there. So far, so good? All right. What would be different if we did a triangle?
Within half. No, you're not.
Okay, so let me ask you that. Hold on. Let me get this set up on Zoom here. What if we had this triangle here? If we used this triangle, do you think the moment of inertia would be, well, what do you think it'd be? Half, more than half, or less than half of this value? So I'm going to rotate this triangle. And let's assume this triangle came from cutting this plate in half, right? Or do you think it's going to be something else entirely? Yeah. Now, what we could do is perhaps compare it to this one. Whoops. Share another triangle. What if we put this plate here? And I think that's the question you were asking, right? Maybe I did, maybe I misunderstood. But let's say we get the moment of inertia for this one is I equals 1/3 m, let's say this is b squared, okay? The moment of inertia for this plate is the same as the rod at the end, right? This is a rod at the center. This plate would be a rod at the end, same. So how would this one compare? You take this thing and you cut it in half right here. You agree that would be cutting the rectangular plate in half? So should the moment of inertia of this be half of this moment of inertia? What do you think?
This is probably something else. I don't know.
Well, let me ask you this. Moment of inertia depends on your distance from the axis to the material. When you cut it in half diagonally, that's not the same as cutting it in half rectangularly, right? If you cut it in half this way, you would exactly cut the moment of inertia in half. But when you cut it this way, what happens to the mass on average? Does it get closer or farther to the axis percentage-wise? Closer. So the moment of inertia of this is actually less than half. Isn't that weird? Whatever. If you care, you can do that. 10.13. And I'm going to point out the answer to that is 1/6 mb squared. But wait, didn't I just say it should be less than half?
It's not exactly.
The mass of this would be less than the mass of this. Agreed? So these formulas can be very tricky, and you could say, like, there's a lot. If we had written these in terms of density, right, this would be sigma 1/2 base times height. Whereas this mass would be sigma base times height. And so we could see this one ends up giving you a 1/12 versus a 1/3. Side note, you're very tired. It's test day. You're not sure what the answer is going to be for a moment of inertia calculation. If in doubt, either put a 12th or a third, right? Don't they all seem to be a 12th or a third? Just a thought. Write a bunch of symbols and then see if I'm tired when I'm great. Don't worry, I won't be. I'll be miserable and angry, but not tired. Okay. Anyways, it's funny how many of these things turn out to be 1/12 or 1/3. That's all I was mentioning. What do you think? Should we take a break? I think it's a good time for a break. Did I do a non-uniform case? We'll do a non-uniform case when we come back. We'll start up with 1014. All right, let's take that break. Last time I held you guys late and that was miserable. 5:37. Okay. I mean, chapter 10 is just gnarly.
You said inertia and torque too.
Yeah. So we're doing torque and inertia tomorrow, basically, in lab. And I'll live stream it too, but I mean, this is kind of the this is as bad as it gets. Really, it's as bad as it gets.
That's good to know.
Yeah. So
Little warning.
to be fair, right, after you can get through, I mean, chapters 9, 10, 11, and 12, it's just rough. But you've got something to build from. So this, I would say this about these chapters. They're harder, but I feel like you know how to study better, you know how to read better, you know how to deal with the equations and my kind of awkward way of speaking better. And as a result, I feel like you can learn more for the same amount of effort. And I think that balances out the difficulty of the material. Right? You're just better at learning and dealing with me. So I think it'll be about equally horrible. Maybe slightly more horrible. That's it. Everybody, you might want to pop to page 62. We want to avoid calculus. Oh, wait. We didn't do a non-uniform case, did we? I said I was going to do non-uniform case. 10 point, sorry about that, page 61. All right. I'm going to at least give you this setup for problem 10.14. And I'm going to tell you this. On test 3, there's always some moment of inertia problem, always. And generally speaking, it's either make a compound object where you get I1 plus I2 plus I3, or I could have an object with a hole in it, and that would be I1 minus I2, right? Or it's like a non-uniform rod like this problem. That's why I want to make sure I show you this. So generally speaking, you get some awkward moment of inertia calculation where it's a bunch of weird objects put together, or an object with a hole, or a non-uniform rod like this.
But it still matter because it's being rotated along the x-axis.
Hold on, let me get in there. I think in this case,
We're doing each.
in part C, we're going to rotate it about the y-axis. Okay? So it will matter. You're right. So if you were saying about the x, you're absolutely right. So if we were rotating this about the x-axis, basically you could say the moment of inertia would be very small. It would be basically mass times the radius of this rod, but that's not what we're doing. We're going to end up rotating about the y-axis.
Earlier in class you said sometimes we treat it as a little cylinder. So that matters because one cylinder is lighter than the other one at the very end.
And yeah. So that's exactly what we're doing, right? Remember when we did the code and we did the center mass and we had different spheres making up a rod? It's the same thing. You can think of this as different cylinders making up the rod, and each cylinder has a slightly different mass. Well, you could think of that as little spheres, right? Same idea. And so you're right, the mass is going to change as we go outwards. In particular, what's a good name for this distance here, this width of my chunk?
Of the chunk? Or-
Yeah, the width of it.
Oh,
dx, because I'm a small amount on the x-axis. What's a good name for this dimension? X, because that's the distance from there. And then if I want to get the moment of inertia, whoops, oh wait, let's read the question carefully. Let me read. Okay, before calculating, should this be bigger? What's up, Don? Hey.
Just trying to stay uniform.
A uniform rod of mass M and length L rotated about the end, not the center, the end would have a 1/3 ml squared. when you look at this, if this is non-uniform with a density given by lambda equals alpha x squared, do you think the moment of inertia should be bigger than or smaller than this value, 0.333 ml squared? What's your gut tell you? Should this have more or less moment of inertia than a uniform rod? Or will it be the same?
Center of mass is gonna be far away from the axis.
What's that?
So the center of mass is gonna be far away from the axis, so
So the mass is far from the axis,
more inertia.
more inertia. We're expecting I should be bigger. This is like a figure skater arms out. Good. Now, you notice I converted this to a decimal. I don't know if you noticed that, but it's a lot easier to compare decimal numbers than fractions. So a lot of times, I'm going to convert this shape factor here to a decimal, all right? Just to help me get, right? Okay, that's our check. It's kind of like check the units. Now it's bigger or smaller than. All right. Well, oh wait, what's the next part? Part B says get the mass. I noticed some people having trouble with this during the coding lab. I want this to be on lock because a lot of times on a test question, I ask this, what's the mass of the rod? Don't overthink it. Mass is the integral of dm. Remember, that's the denominator in your center of mass formula. If you need to get the total mass, integrate dm. Don't overthink it. Well, help me. What's the integral of dm? What's dm for this chunk? 1D, 2D, or 3D object? Yeah, so it's going to be a 1D, so it's a lambda, not a sigma, not a rho. Dx. 1D, use lambda dx. Well, that's pretty easy. Lambda dx is alpha x squared dx. Crap, what are the limits? What is the leftmost value of x I can achieve? 0. What is the rightmost? Did it say? It says the rod has length L. So we're told so what are my limits for this particular problem? What's the leftmost value?
0.
Rightmost?
L.
There's a squeaky ass marker. Do you agree you could do that? Oh, we're told to. Oh, I see. Wait a minute here. Reading B more carefully, it says, we know what M is, figure out alpha. Oh, okay, so I kind of mixed it up. Well, can we use this integral to figure out alpha? Let's find out. I apologize, I didn't read very well. In this case, do you agree the 0 limit drops out? So it's going to be alpha L cubed over 3. Always think about the 0 limit just in case. Well, when I solve that, alpha is equal to so perhaps you were wondering when you were coding, how could I set the constant so that I get the right total mass? And I think, Alonzo, you and I were talking about that, weren't we?
Yeah.
The trick is you can mess around with the constant in your loops until you get the right mass, or you could do an integral and say, well, the constant should be this for this problem. So if you're wondering how you could get the right mass for a constant in the code, this is showing you, or the right constant for mass. All right, so if we know the total mass and length we want, we got it. Now, before we go on, what are the units? kilograms per meter cubed. I just want to confirm that's good before I waste a lot more time. Kilograms per meter cubed times meters squared. Does that equal the right units? What units should I get for a lambda? Kilograms per meter. Sigma was kilograms per meter squared. Does this match up?
Yeah.
Feeling good. Finally, part C. IYY, moment of inertia about the y-axis. In this case, it's going to be r squared dm. But for this problem, r means from the axis to my slice. From the axis to my slice says what? What is r? What is from the axis to my slice? X. So I can rewrite r as x. What is dm? Lambda dx again. Same old shark sandwich. Okay. What are my limits? What's the smallest value of x? 0, or I should say the leftmost, 0 to L, right? X squared times alpha x squared gives me alpha x to the 4th dx. Doing a little magic math here, knowing that in this case, I could tell the 0 limit will drop out. I'm going to get alpha L to the 5th over 5. It's kind of hard to compare that to this, isn't it? How could I make a more direct comparison? We plug in this constant that we figured out. So in general, if you're trying to compare something, it's difficult unless we have a good value for the constant. Now I finally showed you how to get a good value. We do this all the time in 163. When I plug that in, we're going to get 3/5 mL squared. The 3 is up top. The L cubed cancels 2 of the L's. This has the right units of kilogram meter squared. And I can check with a decimal. It's bigger than this one, which is what we expect because more of the mass is far from the axis. All right, what do you think about that? There's a lot to get out of that, I think. Beautiful in its own way. I'm a moment of inertia freak. I love it. I'm sorry you're bored. Okay. I can't help it. It's so entertaining to me. Okay, one last comment here. When I give you a coordinate system and a density, don't change it. I'm going to say that again. When I give you a coordinate system and a density function, don't change it. If you change the coordinate system for a uniform object, fine, we should all get the same answers. But if you change the coordinate system, that would affect the limits, and you would have to correctly modify the density to account for the change in the limits. Good enough? All right, whatever. Now I'll go to page 62. All right, page 62. One of my favorite parts. It's all my favorite. Imagine you have some weird F shape. Lima bean or something weird like that. Okay. Now, this is a plate. And let's say we have some axis that I want to use. And somewhere in here, whatever reason, let's say this is the center of mass. And there's an axis through the center of mass. Whoops. And this is an axis parallel to that axis. Okay? We are going to learn the I about the parallel axis. So that's the parallel symbol, not 11. Is equal to the moment of inertia about the center of mass plus mass times distance squared. The distance is the distance between these axes. By learning this trick, we can avoid having to do calculus for a large number of problems. That is why I'm teaching it to you. We want to use this instead of the calculus, if at all possible, because it's faster. It's just addition and just a quick turn. Students are notorious about getting this wrong for two reasons, and they seem so obvious at first, they don't even seem worth mentioning. But I want to point out, this will only work under two conditions. One, the axes must be parallel. You might be saying, how could I ever screw that up? You might grab the wrong number out of the table with the wrong axis orientation, and then the axes wouldn't be parallel. So sometimes you grab the wrong number out of the table for this one or something. Okay? Two, this is the other one. One axis must use center of mass. Sometimes people will grab the left end of the rod problem out of the table and then screw it all up. You have to use everything to the center of mass, right? So it has to be one axis to the center of mass and the other axis parallel to it. If you can't get both of those conditions met, don't use it. All right? Let's look at 10.16 and see how this matters. Up until now, we've always been using a rod at its end or at the center. So in this case, what if our axis is distance x from the left end? And you remember Alan was mentioning the most common object that we use in these classes is a rod, and what we do is we just pick different spots for the rotation axis. So you've got to do this problem well, okay? The total length of this thing was L. Well, I don't care how tired you are, wake up right now. We got to get this one right, okay? Right, I think I use capital M. All right. Trying to be consistent. Doesn't really matter for this problem, but whatever. Let's try to be consistent. And is it uniform? Yes, uniform. Now, to be fair, do you agree you could use calculus to figure out this moment of inertia? We just showed you how, but then you'd have to figure out the lambdas and get the dm's and get the slice and the integral limits right. With a little bit of practice, we should be able to get this thing. Let's try and use the parallel axis theorem. Well, I need another axis. Where should I draw the other axis? At the center of mass. You got it. So there it is, right? Is that going to work? Is that parallel to the axis drawn? That is.
Oh,
Yeah, and you could debate at that one spot, it is parallel, right? Just right at the board, but this is what I mean by that. I mean, we got to go this way. We have to have the same axis orientation so that the two lines are parallel. So, yeah. All right, so now let's write down the parallel axis theorem. And maybe I'm going to try and color code it to match this example. So I apologize. We used green and purple, right? Just so it matches my sample here. That way I could use exactly the same color coding while it's all on the same board. Sorry about that. Okay. I'm looking for which of these terms in this problem. Do I want md squared? Do I want I center mass, or do I want I parallel? What is the problem asking? Determine I about the axis shown. That was this one. So I want to get this. Agreed? Help me. What is I center of mass? And how did you know that? Where did you get that info? So we looked this one up in a table. That's where you get the table. All right, cool. I think I used capital M, whatever. All right. What's D?
distance.
What distance?
Why not? From.
From what to what?
Oh.
It's the distance. Look at the picture over there.
L/2 minus x.
L over 2 minus x. Does that make sense? It's got to be this distance here, which is not x, not L. It's half, right? This, I'm running out of room. This distance is L over 2. So the D is L. Does that make sense?
Yeah.
So that's the tricks. You basically have to deal with the messiness of real life. And then you got to square that gobbledygook. Ugh. Good. At that point, you got this. How could we check this result? We always like to check if we can think of a good way. What's one way to check everything? Check the units. Kilogram meters squared. Got it. Kilogram meters squared. What's another way to check this result? What do you know any special cases? For example, can you think of a special value, a limiting value of x? 0. If x equals 0, what would the picture look like? a rod about the end.
Yeah.
What is the answer? If x equals 0, what do you get? 1/3, because you get 1/12 ml squared plus m. L over 2 squared is going to be L squared over 4. Common denom, 3/12 plus 1/12, 4/12 equals 1/3. Got it? So having ways to check your work is good. All right, enough on that. All right. You tired yet? Getting there? This is always the time when you guys start to break. When you're up here at the front, it's a lot easier because you're talking the whole time. I apologize that by the way, I apologize I'm lecturing so much this semester. This is not my usual style, but I'm trying to get these stupid videos done. So, right, I got to do this on, it's just different when I have to do this. And so I've kind of devolved into a normal lecture and I hate doing that. Normally I like to do more walking around and stuff, but so my apologies to you guys for having to deal with this class this way. It sucks, but what are you going to do, right? All right, I know what we could do. We could bring Dracula in. Let's look at 10.19. Okay, no more zombies. We're going Dracula here. I used to teach this class in the fall, and so this would fall right around Halloween. So it was a good time to have Dracula show up. But now we're just general blood-sucking fools here. I'm just erasing the board on Zoom, in case you're wondering. So you guys look at 10.19. Alan, if you want to take a loop around, if you're bored, you can loop around. You guys try 10.19 together here. It's going to take me a minute to catch up. Hopefully you have somebody to talk to. Put that down. I'm going to draw it up here. And then you could also do 10.20. So work on both of those. And then Alan, if you want to circle around, you can here. I'll draw them up real quick. Go Bulldogs, huh? I gotta use the symbol L here. My bad. Shading on that. Okay, and the first one what is it? I dotted. This is the claim of what, Dracula? This is Dracula in the first one?
Yeah.
So Dracula claims I dotted equals I solid plus M L over 2 quantity squared. That's Dracula's claim. Dracula's claim. Over here, Frankenstein's claim is that I is equal to 1/2 mass radius squared plus mass radius squared. Because here's the center mass, and this distance is the radius. The physics teacher comes along and says, you guys are jerks. This ain't true. Not true. Why is it not true? Okay, the first one. Anybody want to hazard a guess?
That's like center of mass.
Yeah. Where is the center mass for a triangle?
1/3.
1/3 from the fat end. So we could have used this axis, right? And so we could have done that I center of mass, but the solid is not through the center mass. The parallel axis theorem does not work that way. Okay, good.
Enjoy that.
Yep.
Use the camera.
Oh, crap. Frickin' Zoom. Got it. All right. Sorry about that. All right, but now you can see, in this case, I'll run that through real quick again. So the dotted axis here versus the solid line axis here, well, they fortunately, you guys had it on Zoom, you had it in your workbook, so it wasn't a total waste, but the idea is you have to be using the center mass axis of the parallel axis there. Let's go over here to Frankenstein's claim. Why is Frankenstein wrong too? What's that?
But I just haven't.
Oh, okay. Let's take a second to look at Frankenstein real quick. You got a disk. Frankenstein claims it's 1/2 mr squared plus mr squared. Physics instructor says no, bad Frankenstein. Bad Frankenstein. What about it? The axis. The axis of rotation is this way. For 1/2. What's the result for this axis of rotation? This is a disk.
1/4.
1/4. You see that? So looking at the table, look carefully at the table on whatever page that was, 59. Do you see the two disks in the first column? Right? 1/2 is when you're going through the plane of the disk straight out. This is 1/2. This is 1/4. Got it? All right. There's a lot in there. Now, perpendicular axis theorem. This is not going to be on the year 2022 test. Maybe some other year it might. So if you're watching this in a future year, you know, hey, cool. Oh, Levi, thanks for telling me. Sorry, I missed it, man. Sorry, I missed it, Levi. Thank you for letting me know. Perpendicular axis theorem. It's really cool. If you're into it, let me know later. Great. But it's not going to be on the 2022 test. Go to page 64. Summary. Tried to emphasize this all day. Pay attention closely to the axis or its axis location and orientation. 2. We do the same thing for I1 minus I2 if you got a hole. Basically, try to just grab things out of the table and add them up. Okay. 3. If you can, use the parallel axis theorem. For 2022, we're ignoring the perpendicular axis theorem. There were years I used to put that on tests as like an extra credit question sometimes to see who would actually do the insane perpendicular axis theorem. It's pretty fun, it's pretty beautiful, pretty mathy, whatever. All right, you got all that. I equals the integral of r squared dm. Typically, we do this for and I know sometimes when I'm doing these non-uniform density problems, they seem absurd, and you might feel like they don't have any application in the real world. But there are situations with real life objects that have non-uniform density, and we've seen some of we go like the slinky or all kinds of weird things can show up and be treated as non-uniform density. One of the reasons I really like it is it sets us up for learning how to deal with non-uniform charge distributions in physics 163. So electrical distributions can also be non-uniform. So getting used to deal with density functions, or perhaps you know about chemistry and the p orbitals and the d orbitals and all these different shapes. Those are density functions, right? Electrons are density clouds, probability densities. And so probabilities can also be, so there's a lot of different things that have these densities. So yes, these do show up in different applications at weird times. All right. That's a summary of moment of inertia. So far, so good. All right. One last time. Oh, take a look at the, there's some general info at there. Okay, let's remind ourselves of that. If you have a small moment of inertia, it's easy to change your rotation rate. Okay, it's either to speed it up or slow down its RPMs. Said another way, if you have a small moment of inertia, it's easy to angularly accelerate. You can get an alpha, right? For a small amount of torque, I'll remind you, the sum of torque is equal to I alpha. So the idea is the next thing that we're going to do is we finally figured out how to do this piece, the moment of inertia. It took us 2 hours, but now we know how to figure out the new rotational mass. So finally we can apply forces to things and make them rotate and see what they do. Okay, and that's kind of where we're going. Oh, another fact from this, I forgot to mention this. I want to point this out. Look at this. The I parallel will always be bigger than the center of mass axis. So I center of mass is always smaller than any parallel axis I. The moment of inertia through the center of an object will always be its minimum. So that's a way you can sometimes check your math. The center mass should be the small one compared to the parallel. You can use that to check your math. You know me, I love to do an object with the hole cut out of it. So for review afterwards, you could do the bottom of page 64. Do you see 10.23 and a half and 10.23 and 3/4? In particular, you can calculate 10.23 and a half. Make sure you got center mass versus moment of inertia straight. And then you could try to see what should happen when you flip the location of the hole and see if you can get it right without doing any math. And then you'll know that you know these concepts pretty well. So that's the problems at the bottom of page 64. Enough on that? All right, we got 15 minutes. I'm going to introduce torque. There's more problems in there for you to practice. You can go crazy. Oh my gosh, there's more problems on here. I love me some more. Look at page 67 and 68. I just did that to entertain myself. I don't know what that says about me. You are not required to do that. But if you're interested in how, a common question that I get asked is, well, not that common, is how do they get the 2/5 MR squared? Usually there's some weirdo every year that asks me, right? If you're that weirdo, that page is for you. There's all kinds of, look at the weird techniques I used. I did some weird stuff on page 68. Oh man, there's some weird stuff. Enough said. Okay. You guys can space out for a second while I erase the board, or look at page 69 really quick. I'm going to start on page 69, do a quick summary of torque so that we're set up for success tomorrow. Oh, so much math. I love it. Wrong with me, Dom. I don't know what it is.
I thought you were bagging on the math teaching.
Don't I always? Only because they don't keep the units. But then again, you know those theoretical physicists always do dimensionless, right? Or no, we're weird. Something's just wrong with physicists, but that's cool. Cool with me.
As long as no one-
That's right. Anything you want to tell me about moment of inertia, Dom, while I'm erasing? Or torque or anything?
just work.
Use it a lot in mechanical engineering for sure. I think I only have one mechanical engineer in here. Isn't that crazy?
It's okay.
Yeah. Can't help it if there's only one cool person, right?
Oh.
That's right. We can't all be mechanical. I definitely have a more electrical bent, right? Shocking, I know. Okay, torque, page 69. Let's get something out of these last 15 minutes while we got it. Try and make tomorrow a little easier. Torque. The symbol is tau. We're going to call it a vector. The units for torque are going to be Newton meters. If you've ever used a torque wrench, what are the units on a torque wrench? In this country, usually. Foot pounds, but we write it with no S. Okay? That's why I don't use pounds. I don't want to have to remember that there's no S. Okay, the equation for torque is going to be R cross F. This is not going to mean anything without a picture. So I'm going to draw a picture over here. It is a cross product. We're finally going to start using all that junk from chapter 3. There was a reason I had you do all that crap. It wasn't just for fun. There's going to be a pivot or an axis, however you want to call it. We're going to apply a force at some weird angle, possibly. What does R mean? It means something different in every equation. Have you noticed that? Like R. In this case, R means, see if this paint shows up. From the pivot to the point where the force is applied. And so let's color code this. What's that? Or did you get it? Or no?
That reminds me of Cog 3. Something we did in Cog 3.
Yeah, I'm sure it does. Yeah. Okay, let me make sure I say that before I forget. R is from pivot or axis to point where F apply. Okay. So in theory, I don't need to say any more about this. I know you've got it now, right? Sure. This takes a while to get right. It turns out in practice, this is the first method for figuring out the torque, and it always works. But sometimes it's exceedingly time consuming to do problems this way. Sometimes this is the best way to do a problem. Sometimes it is not, and it's terribly time consuming. So there's another way we could do this. Let me try and go in the same order I did here. We could say the magnitude of the torque is RF sine, well, let me color code this. The magnitude from the pivot to where it's applied times the magnitude of the force. So if you know the distance and the applied force, we just need the angle between. Well, in this case, you might be asking, what is the angle between? You could use this angle right here, theta, and it turns out this is like the only time it's useful, or things you can screw it up and still get it right. You can use either one of these angles because sine of theta equals sine of 180 minus theta. So basically, it's one of those two angles, just grab one. How do you get the direction? Do you remember how you get the direction of a vector without having to do any math from a cross product? Which hand is this? Right hand rule. Watch out. Line up the fingers of your hand. Grab your right hand. Do it. Line up the fingers. Jesus, a tough one. With the R vector. Curl them to the force. So fingers first vector, curl to second vector, thumb in direction of output. First goes to second, goes to output. First, second, output. First, second, output. So I'll just say, this is written on your page there. Fingers are curl to F, thumb direction of tau, right hand. You can't use your left. Bias system. We talked about this already. The advantage of being left-handed is you're better at like beating people up. Yeah. Biologically, they're like, why do left-handers survive? I guess, right? People don't expect punches coming from left-handers the same way, and you can beat people up better. So you may be annoyed doing your cross products, but man, you're going to be ready if you get into a fight club. All right. So you got that going for you. So dumb, right? All right. Third method. Oops. Color code this. R for patch. Trying to color code this and I keep forgetting to color code it. So the direction is going to be the same for rules 2, 3, and 4. So I'm not going to keep writing the right-hand rule because I'm going to run out of space. R perpendicular, you're going to hear me call it R perp for perpendicular. Most people call it a lever arm, but I'm going to call it R perp. Okay, what's R perp? What's R perp? What's the lever arm? Well, let me show you what the lever arm is. This one's sneaky. You could draw what's called the line of action, an imaginary line that goes to infinity through the force. So this is called the line of action, an infinitely long line through the force. Then you can draw something called the perpendicular bisector. That is a line from your pivot point to here that makes a right angle. Let me see if I can get on this here. See how that's supposed to make a right angle there? That is R perp. Now you might be saying, oh, this looks kind of weird. I don't understand why this works. I want to point out, this is theta. What's this angle? Isn't this R sine theta? And you basically get back the same crap. R sine theta is R perp. That's cool. I'm going to try and draw this exact same figure here. I got a force. I'm told that this, okay, this angle is theta. And then I got a pivot right here. Now you got these drawn in your figures there. I'm going to show you method 4. Use the full radius, but you use F perp, the perpendicular amount of force. F perp. Now in this case, let's see if I can do this right. We are now into a new phase of free body diagrams where you need to draw forces at the point where they are applied. Why? If you want to get the torque right, you need to use the point where the force is applied. That means you have to draw your pictures better. If this is the full force, we're also going to split up our force vectors a little differently. This force component would be parallel to the R vector. So I would call this force parallel. This component would be F perpendicular. It's the amount of force perpendicular to the R vector. And now, do you agree this one is going to be F cosine theta in this picture? What's the other one going to be? Notice these are all the same method. Cross product, cross product, cross product, cross product. Here, the sine theta gets grouped with the radius, and you do what's called a lever arm. Here, the sine theta gets grouped with the force, and you just do a force component perpendicular. Now, I claim you will use all 4 of these methods at different times. I have, but I don't know. Dom, which two, like, do you normally use this method and this method, or do you use the lever? What do you use most in the engineering classes, Dom?
1, 2, 3.
1, 2, or 3 most of the time. Yeah. There's a weird example at the bottom of the page. Yeah, I call it occasionally useful style, where I actually use 3 and 4 simultaneously. I split the force into components and do separate lever arms for each component. But I have a feeling you probably do that sometimes too. So basically, I wish I didn't have to teach this because it's a lot, right? But basically, all of these methods come into play. To be fair, if you had to learn just one, this one. And then after that, probably this one. And these will get you through this class. But as you move onwards, you probably are going to need to know these more and more and more. Okay? All right. There's a bunch of crap on here on this board here. We got a few minutes. Let's see if there's anything else that I've missed. See that stuff to memorize there? In the middle of the page, stuff to memorize. There's one important thing that I want to get that's not up here. If line of action through pivot torque equals 0. This is one that is not really, doesn't have a place up here, but it's something that's extremely useful. Obviously, you could say, well, if the R vector is 0, there should be no torque. But a stronger, more general condition is actually this one. Anytime the line of action goes through the pivot. Obviously, if R vector is 0, you get line of action through the pivot. But look at this force component. The line of action for force parallel goes through the pivot. This one causes no torque. And so what you're doing when you do this force perp is you're splitting into no torque component, torque component. Okay. Done. Let's call it good. I'll end on time for once. We're going to be working hard tomorrow. If you can, read or watch a video or read a book or something, or just get a good night's sleep and lots of food so you're ready to rock. All right. Oh my gosh, I appreciate all the hard work today.